In this lecture, we're going to introduce decoders, multiplexers, and tristate buffers and their relation between them. So we introduced multiplexers in a previous lecture where we talked about incomplete truth tables, but it's possible to construct multiplexers using a circuit that is called a decoder. What is a decoder? Let's take the high-level symbol here and say we have two possible inputs, S1 and S0, and now we have 1, 2, 3, 4 possible outputs. Call this O, yes, O3, O2, O1, and O0. Let us look here. We have 4 input combinations. For S1 and S0. So we use these to select the output line. To select output line. This is our decoder, 2 to 4. So it takes 2 inputs and outputs 4 output lines. How does the truth table look? Well, we have S1 and S0 as input, and we have 4 outputs. O3, O2, O1, and O0. 0, 0, 0, 1, 1, 0, 1, 1 as our 4 input combinations. And we output a 1 here, and zeros for the rest on the first, a 1 for O1, and zeros for O0, 2, and O3. For input 1, 0, we output a 1 for O2, zeros for the rest. And input S1, S0 equals 1, we output O3 equals 1, and zeros for the rest. So the output is active high here. Now for a arbitrary decoder with input K, decoder K, this would be the decoder 2. You have K inputs and 2 to the power of K outputs. And the truth table is generated by selecting the output line based on the input. So for input S equals the bit vector sk minus 1 down to S0, select output number O sub S. There are 2 ways for this circuit to be implemented: output active high and output active low. How does this look? Let's look at the decoder 2. with an output active low. We have S1 and S0 for inputs, and we have O3, O2, O1, and O0. Possible input combinations are 0, 0, 0, 1, 1, 0, 1, 1. What makes this different from the active high output is that the active low inputs set the outputs to 0 instead of 1. So we have output 0 for input 0, 0, and all other inputs for O1, O2, and O3 are 1. If we have input 0, 1, then output 1 is 0, and all other inputs are 1. For input 1, 0, O2 is 0, all other outputs are 1, and the pattern continues. Input 1, 1, output 3 is 0, and the remaining outputs are set to 1. Depending on circuit implementations, you can use a decoder with output active low or output active high. Now, implementing a decoder in digital logic is fairly straightforward. You can use AND gates for output active high or NAND gates for output active low. So let's do a decoder 2 in digital logic. Say we have S1, S1 prime, S0, S0 prime. And we are going to have 4 possible outputs. So let's set this to O3, O2, set this to O1, and this to O0. And now, for O3, this is 1, 1. O2, we have S1 equals 1, S0 equals 0, so S0 prime. O1, S1 is 0, so S1 prime, and S0 is 1. And then for output 0, we have input S1 prime and input S0 prime. And this will give us an active high decoder 2 implementation. Running out of space here. You can add inverters for S1 prime and S0 prime if you do not have the inversions of S1 and S0. This depends entirely upon the implementation of the digital logic that you are using. What if we wanted an active low decoder 2? Let's do the implementation for that. Well, we have S1 and S1 prime, S0, and S0 prime again. For the active low implementation, we use 4 NAND gates. This is for the decoder 2. For decoder 3, you would use 2 to the power of 3 NAND gates. For decoder 4, 2 to the power of 4 NAND gates, or 16 NAND gates. So the pattern holds. So this would be O3, O2, O1, and O0, respectively. 1, 1, 1, 0, 0, 1, 0, 0. And this would give us our active low output decoder. There is one other possible symbol or input signal that could come to a decoder, which is called the enable signal. The enable signal sets whether the decoder is outputting a signal or not. So if we have an enable signal and we have if we have an enable signal and we have S1, S0, and then our 4 outputs, O3 to O0. You could implement it by just adding another line, input line, with S1 and S0. Let's draw all 5 input lines here. So this is our enable. S1, oh. Let's redraw this so we have a little bit more space. Enable S1, S1 prime, S0, S0 prime, and then we draw our 4 AND gates again. So O3, O2, O1, and O0. Now we need 1, 1, 1, 0, 0, 1, and 0, 0 inputs. How does the enable signal work? Well, we don't wish to output anything unless the enable signal is high. So we just connect the enable signal to all of these AND gates and AND that with our input, with our other inputs, and this will enable or disable the output from the decoder. Keep in mind that sometimes EN is active low. In other words, need to invert en first. So bear this in mind. And you may need to do some thinking if you wish to get the output inversions for an active low output decoder to work with an active high or active low enable signal. So think very carefully about the application and the truth tables that are specified in the data sheet if you are using somebody else's encoder, or decoder rather, or if you are implementing your own. Now, why are we interested in using decoders? Because decoders are the basis for handling multiplexers. Well, a multiplexer, we can recall the functionality by drawing the schematic symbol for one. Say we have 3 or 4 possible inputs on our multiplexer. Call these inputs A, B, C, D. And then we have selection signals S1 and S0. Selection signals S1 and S0 are used to select which of these values are sent to Y. So Y is equal to S1, S0, A, or S1, S0 prime B, or S0, 1 prime S0 C, or S1 prime S0 prime D. How does this look when we implement it? Well, it is 4 AND gates driving an OR gate. So we'll take S0, S0 prime, S1, and S1 prime. Give ourselves a little more space, and let's label it at the bottom. S1 prime, S0, S0 prime. And we can connect 1, 1, 1, whoops, 1, 0, 0, 1, and 0, 0. And we also AND each of these with the respective input signal. So A, if we have input 1, 1, B, if we have input 1, 0, C, if we have input 0, 1, and D, if we have input 0, 0. Now we can OR all of these AND terms together. This gives us the output of our multiplexer. Very straightforward implementation of this multiplexer of MUX4. Label Y. Notice that the things that we have different between the multiplexer and the decoder are this OR gate and the inclusion of these AND input signals. We also have extra inputs on each AND gate. So it is possible to implement this using a decoder. So let's say we have a decoder with inputs S1 and S0. Let's bring our selection bits up. And now we have 2, 3, whoops. Let's bring these up higher instead. We'll place 1 down here. So we'll have input A here, input B here, input C, and input D. We will then AND with output 3, output 2, output 1, and output 0, respectively. And then we can OR these together. And we have our multiplexer. Notice that we basically broke out these 4 AND operations from the multiplexer operation here. Remember, A and, well, let's not use A, let's use T, U, and V. So T and U and V is equal to, on a 3-input AND gate, is equal to T ANDed with U, ANDed with V. So this would be a 2-input and 2 in, and this would be 3 in AND. So all we're doing is using associative property of AND operations. So when we implement with the decoder, it's fairly straightforward if we have a decoder for 2-input NANDs and an OR gate. But what if we wish to skip using the OR gate, if at all possible? A 4-input gate can be expensive. And the 2-input gates, if we could reduce those to 1-input logic gates or buffers, that would be ideal. And one technique that we can use to do that is to use the Tristate buffer. So what is a Tristate buffer? Well, think of an inverter, right? You have an input A, and then you will output A prime here. A very straightforward logic gate. If you have a second inverter, B, it will output B prime, right? Let's say, however, that we implement Instead of with an inversion, we don't invert and we have buffers instead. So we have A and B. Then it would output signals A and B respectively. Now, let's consider a problem. We are unable to tie these two circuits together, the buffers, or the outputs of any logic gates together. Outputs tied together. What this does is it gives us a short circuit. What does a short circuit mean? Well, think about a short circuit and what happens when you connect your power to ground. Basically, they tell you not to stick a wire into the wall socket when you're growing up. And the reason is that you're going to get smoke, heat, and light. Smoke, heat, and light, lots of energy is going to suddenly rush through, and it's going to damage and possibly destroy the circuit. More often than not, it destroys the circuit. So shorting these outputs together is not ideal. However, it's possible to use something that's called a tristate buffer here, and you have A, and then you have your control signal, let's say K, and then the output is either A, if K equals 0, or the tristate value Z if K equals 1. The Z tristate means disconnected. A better way to represent this circuit may be to say you have a buffer and a controllable switch, where K controls this switch here, and you have input A, and then this output O can be disconnected. O can be disconnected by K. Now, what is very, very nice about this is you can connect outputs together. Let's use this to advantage with the decoder here. What happens if we place 1, 2, 3, 4 tri-state buffers, like so, and then connect the outputs together? And then we connect the inputs to A, B, C, and D respectively. Well, we can then connect a decoder. We're going to use here an active low decoder. S1, S0, and then we connect the decoder to outputs O3, O2, O1, and O0 to the control signals for these four tri-state buffers. What is nice is that a decoder ensures only one output will be enabled at one time, so there are no conflicts. What does this mean? Y will equal A if S1 equals 1, S2 equals 1. Y equals B if S1 equals 1, S2 equals 0. Y equals C if S1 equals 0, S0. Oh, I'm marking S2 here. These should be S0s rather. So if S1 equals 1, S0 equals 1, S1 equals 1, S0 equals 0, Y equals C if S1 equals 0 and S0 equals 1, Y equals D if S1 equals 0 and S0 equals 0. And we have implementation of a mux here. And it's probably one of the more efficient implementations that you can find of a mux. So when you're building circuits and you need to select one of many signals, probably the more efficient method of doing this, if you have more than 4 input signals, more than A, B, C, and D, but say 32 possible signals, you could use tri-state buffers to implement them instead, to implement the multiplexing instead. This will be space efficient and power efficient and perhaps even in some cases more speed efficient. Some cases, depending upon the implementation.